So, hello everyone. My name is Itamar Holder. This is Igor Bezuch, and we've been colleagues for a few years now. We are long-standing KubeVirt developers and approvers. And this is our cool medieval talk about high-density VMs in OpenShift, or the pilgrimage to native Kubernetes swap. So what we're going to talk about today, or the map of the realm, is the quest for VM density, and we'll talk about why this is important in a minute. And then the wasp-agent crusade, or our solution until we can use Kubernetes swap, and then the transition to Kubernetes swap, and finally some data and numbers to prove this is working. So why is higher VM density even important? So VMs are very different from containers. While containers are designed to have a very small state and a very consigned state, VMs carry just a huge state that you don't generally need it all, right? It carries the whole kernel and the drivers and the pre-installed applications. And when you're running a big amount of VM instances on your cluster, you have a lot of duplicated data that you don't really need. So that's basically the first use case. Another thing is that bare metal users that use bare metal servers basically face an inflexibility in the sense that scaling the number of nodes in your cluster is difficult and sometimes even impossible. So you have to manage your resources more efficiently. Another thing is that if you have very fast storage, like NVMe, you can use it as effective extended RAM. And this is basically why it's important. Now, VMs and containers are almost the opposite in the sense of how they limit themselves. So with VMs, when you ask for a certain amount of memory, you are inherently limited to this amount of memory, which is kind of the opposite with containers that are, by default, can just use all of the host resources until they decide to limit themselves, right? So in KubeVirt, what we do is basically we run VMs inside of containers. So how do we manage that? And basically the trick is that the pod, to achieve higher density, the pod will just request less memory than the VM really needs. So this is how it looks like. Imagine that this box is the container that we run the VM in. Simplistically speaking, we run two things inside a container. First, we run the actual guest, and the guest has the guest memory that it needs. And on top of that, we have the virtualization infrastructure, which basically is the hypervisor and KubeVirt customized code that we need to manage it all. Slides are disappearing and reappearing for some reason. So basically the memory requests that are defined for this container are the guest memory plus the virtualization overhead. And when we want to achieve higher density, we basically do this. We just reduce the amount of memory requests, so we can just reserve less memory than we would actually need if we would use all of the data. And implicitly, we are building upon deduplicating this data somehow, and I'll get to that in a second. And in order to configure this, we have a configurable that's called the overcommitment ratio. And the idea is that basically, let's say that you define a 50, a ratio of 50, then a VM that is requesting 10 gigs of memory will actually get 5 plus overhead. So you have more or less 50% of the memory that you can use by other VMs. But as I said before, this memory would somehow need to get deduplicated. And we have a few mechanisms for that. So the first one is called FPR, or free page reporting. And here the idea is that the guest would report the free pages back to the hypervisor, and then the hypervisor would be able to reuse these pages in the host level for other purposes. We also use KSM, or kernel same page merging. Here the idea is that the kernel will try to find identical pages and basically merge them all into a single copy on write page. Now this is a bit risky in the sense that if this page is not needed at all, that's fine. But if the instances would try to write to this page, what will happen is that we would need to duplicate it again, right? If it happens within a lot of instances in parallel, what will happen is that suddenly we have to allocate much more memory, which means we risk having kills from all over the place, and the slides disappeared again.
So apparently they return.
Apparently.
Just have a bit of faith. They always come back. Okay. The final mechanism is swap memory. So swap is somewhat complementary to KSM, in the sense that when KSM needs to duplicate the data, we can just take data that we don't need and swap it away to the storage, which is usually pretty big. And swap is pretty great for this purpose because if the data is really never needed, then it would just reside in swap forever, and this is a great way to tackle the deduplication. So back in the day, the situation was that Kubernetes was still supported swap under beta, and basically we couldn't use beta features in production. But it was a problem because there was an eager customer demand to use swap and higher density, and we needed an intermediate solution. By the way, I did a talk about node swap on KubeCon, so you're invited to watch this talk. But basically the idea is that we would come up with a wasp-agent, which is like abbreviation of swap, and basically we had two goals there. One is to deliver swap without touching kubelet, without, and basically by bypassing the Kubernetes components. And that's once the swap will be GA'd in Kubernetes, the transition will be smooth and seamless, and the users won't even notice it. But how do we actually do that? How do we bypass kubelet and actually edit stuff behind its legs? So we decided to use OCI runtime hooks. And basically these are external binaries that run at certain container hook points that basically can interfere with how OCI does things, and basically this is how we did it. So back in the day we had two swap behaviors in Kubernetes. One is called unlimited swap and the other limited swap. Let's talk about unlimited swap first, although it was since removed from Kubernetes, but back in the day it was the main one. And to support it, we had to basically write max into the cgroup knob that's called memory.swap.max. That basically means that the container can use as much as swap as they want, and they're basically not limited with swap usage. And there were some exceptions to that. So pods with burstable QoS, or high priority pods, or pods with memory limits that are equal to the memory request are excluded for using swap for many reasons, but we wanted to stick to stay as similar as we can to the Kubernetes implementation, so that's what we tried to do. So to reiterate, we tried to take an OCI hook, write max to the right cgroup knob, and exclude this kind of pods. And this is easy, right? Right? Wrong. Okay, so if this will just be solved this way, the presentation would be ended here, but the first problem emerged. So systemd strikes back. So what we did is basically write the cgroup value straight into the cgroup knob through cgroupfs, right? Just writing it straight to the file. But OpenShift uses the systemd cgroup driver. And it turns out that systemd maintains a file, which is like the desired state for the container. And then whenever it applies anything, it basically reconciled the actual state to the desired state, which means that systemd was continuously fighting with us, overriding our values. So this was a problem. So what we ended up doing is use OCI update. Basically, in the first implementation, we used OCI as a library, and now we understood we need to use it as a binary, because when you use it in a binary, you have the OCI update command, which edits the desired state file, basically syncs with systemd and makes it aware of our changes. The problem is that we had to change the hook from pre-start to post-start, because before the container even exists, this file doesn't exist. So we have to basically make the change after the container is created. So this is it, right? It's fixed, right? Right. Wrong again, right? So more problems emerged. We got to the cascading failure, which basically some containers are short-lived, especially init containers in some situations, which means that basically now we have a race, which systemd kills the container before we actually get to update it by the OCI hook, which leads to errors. The problem is that the errors would eventually pop up all the way to kubelet, and kubelet will say, okay, I don't know, something went wrong with the OCI, I need to terminate this pod, and basically this caused problems all over the place. And we said, okay, let's solve it with a simple solution. We will just check if the container's PID1 is still alive, and if not, we assume it was short-lived, and we'll just skip the configuration entirely. As a side question, maybe you're thinking to yourself, why didn't we use NRI? Why use OCI hooks? And NRI sounds like a perfect fit, and it is a perfect fit. And NRI is a great piece of technology. The reason that we didn't use it back in the day is that it was too new and unstable to use. And fun fact is that the version 1, which is supposed to be the official stable version, is still not released. But NRI is definitely eventually going to be the right tool for this kind of task. Either way, we said, as I said, an unlimited swap was eventually removed completely from Kubernetes, and we needed to support limited swap. Now, the idea with limited swap is that the limit itself is calculated by this formula that I don't want you to read, because simplistically what it means is that it's proportionate to the memory request and the node size. So, for example, if your container will request 50% of the whole node capacity, it would be limited to 50% of the swap capacity. So it's just proportionate to one another. So how did we do that? So we did it with two phases. First of all, we said, okay, OCI hooks are problematic. We understood it by now. We wanted to narrow them down as much as we could. Basically, in the first phase, the OCI hook did what it did previously, just tried to support unlimited swap. By the way, what's the reason for that is that the OCI lacks context. So, for example, it just doesn't know swap capacity or stuff like that. It's just, it only is aware to the context of the specific container we're trying to edit. And so in the first phase, just try to do unlimited swap as we did before. And in the second phase, we created a simple controller, privilege node local controller, that basically would be aware of the swap limit and swap size and could basically calculate the right limit dynamically. Now there is a small twist here that basically the container starts with unlimited swap, and then we add the limit right away. So it's possible that for maybe second or two it will be unlimited with swap, but this is nothing to worry about really, because first of all, swap is slow enough to bloat right away in a second, and second of all, when we do set the limit on cgroup, if you breach the limit, the container will just be killed right away. So next we got to deal with evictions, and I'll let Igor take it away from here.
Yeah. Thank you, Itamar. So now that we saw that we have the orthogonal solution for Kubernetes swap, let's talk about evictions. Kubelet has a component called eviction manager, and basically what it does, it's constantly tracking the utilization of critical resources such as CPU and memory. When the available memory drops below the threshold defined in kubelet, kubelet will start to kill pods in order to save the node from crashing. Now, what we saw is that the eviction manager interferes with swap. Now, pods don't have the opportunity to get swapped, and they are killed immediately. So what we tried to solve is to try to trigger swap before eviction will happen. And we went to the cgroup FS. So we discovered that there is an interface file called memory high. It's a threshold that when your application goes beyond the threshold, direct reclaim of memory begins. So we were thinking, so we saw that the swap is actually happening on the processes that are inside the cgroup. So we were thinking, okay, we found the solution, right? So it was like pretty easy, right? So wrong. The problem with that cgroup FS is that what happens when you don't have free memory? The reclaim will happen forever. The kernel will scan the pages, and you will hit, like, your application will basically block on memory allocation. So what we found is that we had random timeouts from application that's running inside the pod during the memory reclamation. And we found out that in the kernel docs, they are telling you to create a custom external monitor that will solve the memory shortage while the kernel scans the memory when the memory high threshold is reached. So we tried, we were thinking we'll stop fight with cgroup FS. We went to the kernel tuning solution. Now, evictions made right, we were thinking that we would need to eventually sync the kernel swap thresholds with kubelet thresholds. KSwapD has few thresholds called watermarks, and we were thinking to create an ordered escalation scenario where first you have swap. Then if it doesn't help, memory keeps drop, we will take the kubelet eviction approach. And we will leave the direct reclaim and the om kill for as a last resort, because it will kill the workload. Okay, so a small recap. What have we learned so far? Relying on beta features can be tricky. Even that you are almost sure that implementation will not change, you follow the enhancement proposal, you see that almost there from beta to GA, things can change in the last minute. So when implementing an orthogonal solution to Kubernetes feature for fast adoption, it can be tricky. We saw that OCI hooks, in general, they are great, but not for some certain cases, especially when you try to configure yourself from your own context, when it's about configuring your own resources. And we saw that sometimes from cgroup FS you cannot find the ultimate solution, and for that you have the well-known kernel parameters that are already there for a long time and for a good reason. Okay, so now we have Kubernetes GA. Obviously, like it was in Kubernetes 1.34, we have OpenShift, which is the downstream, our downstream of Kubernetes. So we were thinking, okay, we will just rebase. We will take that feature and we can deprecate wasp-agent, which will, of course, save our time as the maintainers. Right? So once again, wrong. And why is that? Because when an upstream feature is GA'd and you rebase it, it doesn't mean that necessarily you as a team would like to give support for it for your customers. And in our case, OpenShift users were not so eager to use swap for pods on one hand. On the other hand, KubeVirt, which is us, we rely on OpenShift. So we had to come up with a solution and to convince the teams and to have some agreement via API that we will enable the swap feature in kubelet when our operator will be installed. So that's what it basically did. In the small details, we are using like drop-in files for kubelet configuration. As far as we are being deployed, we put the configuration there. So, okay, so we got swap GA. We have a way to opt in for that. Now we need to decide what to swap and what not. And we were decided that critical services such as CRI-O, kubelet, and SSH, they cannot tolerate timeouts due to I/O. So we fenced them from swapping. And it was actually easily achieved because in our operating system in Fedora, you have the system, the cgroup hierarchy. The critical services were under the system slice, so we defined CPU and I/O priorities for them, and that was our solution for that. Now, another question is where to swap. In order to do that, you have to provision, which means you have to create, allocate, and prepare the swap storage. You have basically two options while you're installing the cluster from scratch, or if you want to opt in for storage, for swap, on a running cluster. So there is terminology like day 0 and day 1. Day 0 is like installation, provision time, and day 1 is on a running cluster. And both of them actually tricky because nowadays I'm not familiar with an installer of Kubernetes that can allocate swap as part of the OS installation automation. And about day 1, it also can be tricky because Kubernetes can run almost on every distribution, and for the cloud there are two approaches when it's mutable OS or immutable. Mutable OS means that you can change the rootfs while your cluster is already running. It's a good thing because you can then experiment with things, you can create some specific scenario only on one node in the cluster, but usually from operational perspective it is not that good because you have to have an external configuration management tool, and if you don't have one, you can run into configuration drifts and you have a snowflake effect when issues are coming. On the immutable OS side, it means when after the OS installation, the rootfs is sealed, and there are options to configure to customize the rootfs. There is a specification, maybe you're familiar with it, the ignition specification. What was a surprise to us that not all the distributions follow the ignition. Some of them are still in Cloud init, and some of them are sealed, and they are using some custom API. Once again, the pros of immutable OS, it's easy to administer, easy to operate on the cloud in production. It's very predictable. You cannot drift with a configuration change. On the other side, if you want to do some specific configuration, you will have a hard time, and you have to create a specific file, and to make sure it will be applied on the node, and the node needs to be basically reprovisioned, so you have to move the workloads out from that node, so it's not optimal. So we decided that there is no unified solution for the provisioning question. We decided to focus on our domain. We run on Red Hat Core OS. It's based on Fedora Core OS. It's an immutable distribution. And we can control the contents using an operator that comes with OpenShift, which is called machine config operator. So we basically created the custom resources that describing our provisioning system, the units and configurations, and just deployed it on the cluster. And it can be used both on day 1 and on day 0 as part of the installation. You can put custom machine configs resources as part of the post-installation step. Okay, so the current state of the realm, starting with OpenShift Virtualization 4.22, you can opt in for Kubernetes swap. An important tip from us is that when you are about to provision swap, do not forget to set this flag. This is another safeguard that still exists in kubelet. Also, Kubernetes swap is G8. If you will provision swap and will not put this flag, your kubelet will crash. Now, future work that we think to do in Kubernetes about swap, we think that eviction manager that I was talking about earlier, it is profitable for it to be swap aware from, for example, I/O latencies and stuff like that. We also think that a specific workload, if he wants to opt out from swap, we should give him this ability through the API. And also for the Kubernetes scheduler to be aware of swap as a resource consideration when scheduling the pods. And now I would like to share the real numbers, the real experience from VM higher density with all that solution that we presented to you. So like a short summary, we were testing it, our performance team was testing it on a cluster of OpenShift Virtualization. The worker node had 64 cores, 192 gig RAM, and 3 storage devices, NVMe devices. The rootfs was on a separate device. The swap has a dedicated NVMe device. The VM had like 6 vCPUs and 20 gigs of RAM. Now, we conducted 4 tests. Each test had a different production database. And each step of the test was starting from one VM with the database and adding more VMs until we reach a certain percentage of overcommit. And what we saw is basically, so what you can see here is the 5 groups. So each color represents a test, and each color also is a different database. So the most interesting part is the right side, that you can see on the right side there was an overcommit scenario of 12.5%, and the performance, it was an impact, but for a certain databases there was no such an impact. So workloads kept working, the node was stable, we didn't see OM kills, we didn't see any other side effects. So, yeah. Basically, there are few conclusions about that we reached the finish line. We managed to create a good overcommit solution with swap, with databases that can function even under certain I/O rate against NVMe devices. And the most important maybe thing is that NVMe is the key here, that NVMe device, it's not like in the old times. NVMe is faster, and in certain cases, I mean, in most of the cases, it could be a reliable storage for swap. So we made it, right? Yeah, actually, right. So a short recap. We saw how all the dots are connected. We saw that memory overcommit, there are mechanisms that can help with it. It was KSM, FPR, and swap. We also showed you how you can create an orthogonal solution to node level, low level features if you would like to experiment with some new C group or kernel tuning. There are these hooks that we showed, NRI, OCI, and we saw the drawbacks maybe of OCI when not to use it. And yeah, we shared the real numbers with you. So yeah, thank you. Thank you.
Any questions?
When you were talking about the limited and unlimited swap, why do you believe there's value in the limited swap option when the VMs are pretty well mounted to the consumption?
The question was, why did we set a swap limit at all? Because VMs are bounded by memory. And this is correct. The thing is that, I was implementing swap support to Kubernetes, and we tried to mimic the same logic. Now, in Kubernetes, they don't care about VMs, right? They care about containers. It did need to apply across the board to all of the containers in the cluster. So we just followed the same implementation to mimic them. That's basically the reason. You're right that if we had only VMs, maybe we could have done things differently. Any other questions? Yep.
You mentioned that you have basically 2 phases. Like first, local swap and then switch to limited. Does it work well with scale? Like if you have a bunch of all at the same time.
Yeah. So the question is, we moved to we used unlimited swap and limited swap, and how all of this scales, right? This is one of the one of the reasons that there were many problems with unlimited swap. One of the reasons is that basically, when you're doing things like that, it basically means that order is important. So if the first container is spawned and then starts to use swap, and then it captures a lot of swap memory, the other container cannot use it because swap is already full. The whole idea with limited swap is that it eliminates this problem, because because it basically, because it's proportionate to the memory request, you're able to use the same percentage as you can use like with the memory request. That's why basically it means that ordering becomes insignificant, and that's why it works with scale, right? So let's, I mean, if you have like 5 containers, right? If each requests like 20% of the memory of the node, each one will just get 20% of the swap limit. So it doesn't really matter which one comes first. That's basically the idea. Any other questions? Going once, going twice? All right, thank you very much. Have a great rest of the day.
Thank you.